have to warn you that the talk is being recorded and people may be participating remotely.
Ah, I see. Okay.
But this is also some kind of recording device, so
got it.
only make rude remarks about people if you want to be
on
record.
I was definitely planning on that.
There was this famous episode, probably before you were born, where President Reagan didn't realize that the mic was still on, and he basically said, you know,
hi. Nice to meet you, Archana.
So he said basically that's it. Call a strategic air command. We're bombing Russia in 5 minutes.
Luckily, I have no such power.
I remember this from the parent side.
Yes. I don't know why it caused a certain amount of anxiety and confusion in the world.
It was kind of scary.
I can believe that it was scary here too, but probably more scary for you. All right, so I guess we're going to wait for the statutory couple of minutes after.
Sure.
And just let you know, the recording is already starting.
Recording is already starting. All right.
Okay.
Thank you, Rob.
Hey, Mitri. Good morning. Morning.
Right, and so as I said to Archana, I have to be downtown. So Dimitri, you're going to do the chalk talk thing?
Yeah.
Yeah, right.
Yeah. Archana will do the chalk talk.
Yes.
I hope. I was.
And Andrea, you and Afi can take her, I hope, to dinner.
Yeah.
You know, I'll meet you there. But
That's great. Yeah.
That's great. And
So,
Afi is, I think, he was coming back on an overnight flight or something, so he'll be here a little later.
Okay.
Great. I'd like to say.
Okay.
where was he flying in from? I saw him in Boston. I saw him in Boston.
Yeah. All I know is that he was away yesterday and was coming back either late tonight or overnight, and would be here today, assuming that the airlines don't betray him. Okay, so why don't we start? So today, it's our pleasure to have Dr. Archana Raja, who is a Columbia alumna. You did your thesis with Lou Bruce and Tony Hines and various other shady characters of that nature. And then moved to Stanford briefly and is now at Berkeley, and she's going to tell us about tuning energy levels and energy flow in nanomaterials. Archana.
Thank you so much for the invitation. It's a pleasure to be back. So I'm going to tell you a little bit about the work I did at Columbia and some of the work I'm doing now at Berkeley, tuning nanomaterials using the external environment. So one of the early drivers of nanoscience was measuring the particle in a box and creating artificial atoms at the limit of 2 to 7 nanometers, making these things called quantum dots, where you change their size of the box, in this case, size of the dot, and you can robustly change the optical and electronic properties of the material. Now, there's another effect that happens to molecules, which is that they strongly interact with the environment. So this is a picture of this particular complicated molecule sitting in different solvents, showing very different colors. Now, what would be the equivalent of that, and can we sort of mimic this effect in nanoscale materials, and could that drive interesting science here? So we have a number of building blocks that are available today, from quantum dots, which are 0-dimensional, fullerenes, 1D systems, they call them nanotubes, nanowires, and the youngest in the family that people in Columbia especially are familiar with, and transition like alkylogenides, and this family continues to grow. But I will be focusing primarily on the semiconducting variety of these materials, which are like MOS2, WS2, or the selenides, and using graphene and hexagonal boron nitride, which are metallic and insulating to interact with them. And of course, if you've been at APS last week, there's a whole explosion of other material systems, which makes these materials superconducting, magnetic, and whatever you want is available. But one of the reasons why MOS2, which is a fairly old material, there were reviews in the 70s on the excitonic properties of these materials in the bulk system. So they're indirect gap in the bulk material. So this is the layers of MOS2 stacked on top of each other, looking at it from the side. So the gamma point has contributions from the chalcogen or p orbitals, which are sticking out of plane. So these are the chalcogen atoms like sulfur or selenium. And high symmetry points like the K point, M point, etc. have metal d orbital contributions that are in the plane of the material. So let's see what happens when you make this thinner and thinner, and many of you should be familiar with this, since it was one of the first demonstrations was done here about 9 years ago. So as you thin this material down, you have quantum confinement effects that kick in on the out of plane direction. So this indirect gap, which is contributions from the chalcogen orbital, starts to increase, and at some point becomes larger than the direct gap, and that point is when it becomes atomically thin. So why is a direct gap semiconductor interesting to any of us? Because of this. So you have a monolayer and a few layers sitting on a substrate with holes, and if you were to excite these layers, you see that there's much stronger light emission coming from the single layers than few layers. And already here you can see the sample that's sitting on top of the holes emits brighter light, so it's sort of more sensitive to the environment, and this sort of foreshadows some of the things that I'm going to be talking about today. And you could take these materials and make all kinds of heterostructures. They're never almost ever used just in isolation. So you can put together an arbitrary stack of these materials, which is something completely new for systems where traditionally you had to care about how the covalent bonds and so on work. But here you can just slap things on top of each other, which are superconducting, semiconducting, and so on. And these are truly atomically precise modulation of properties, especially for the 2D systems. If you notice, there are no dangling bonds, graphene too. And you have this additional degree of freedom, or the interlayer twist, which is very exciting, especially in the past year or so, because of superconductivity, Moire excitons, and so on. So the part that I'm going to try and convince you today is that controlling the environment of this system that's atomically thin, and the field lines, or sensing the environment, is important both from the fundamental and applicative points of view. Especially, again, to reiterate, almost always you're going to use these materials embedded in some sort of a dielectric environment for any kind of device or investigative system. So I'm going to talk about three things in today's talk. The first part will be about Coulomb engineering of the band gap and excitons in 2D materials, followed by energy transfer and enhancement of exciton-phonon interactions when you add one layer on top of another. So band gap engineering, like the laser pointer that I'm holding today, a lot of the electronics, everything has been driven by engineering the band gap in the solid state. And if you want to boil down to the core of what it is you have electrons in your band and you're tuning the interaction between these electrons, you can change the band gap. So this is just a cartoon of field lines between two electrons in the material. And in the bulk case, if you were to dope it, you can screen this interaction, change the gap. You can alloy things, you can change the gap that way, or you strain the lattice, and also leads to band gap engineering. However, at the 2D limit, you can do nothing at all to the material, but just change the environment, because you can see that these cartoon field lines are just leaking out of your system, and you can change the electronic properties of the material this way. So in this part of the talk, I'm going to call this Coulomb engineering. And of course, if you're going to change the properties of the material by placing something on it, there should be a good way to sort of measure this without interfering with the material itself. And one good way to do that is through optics and through actually following the excitons. And excitons are also consequence of the Coulomb interaction. If you were to
I'm sorry, I didn't understand one thing.
Yeah.
So you say in 2D,
Yeah.
it doesn't matter how much I strain it, the band gap doesn't change?
No,
That's not what you said.
It does. I'm saying that you can change the band gap by all of those things, perturb the material in some way, but you can change it without doing any of that.
In addition to?
In addition.
Okay, got it.
And this effect can be sometimes larger than some of those effects, and that's what I'm going to show you. So you can excite an electron from the valence band into the conduction band, and this is a schematic optical absorption spectrum. And if you have a 2D density of states, you have a step-like function where you have the quasi-particles at that edge. But these particles see each other, the electron and the hole, and you form a complex that's more stable than these three particles. It's called the exciton, and it's stabilized with respect to this band edge by the so-called binding energy. So if we were to calculate the numbers for the binding energy, so in the hydrogen case, familiar number is 13.6 eV, which we learned in high school, and this sort of the ingredients that go into this is the effective mass, the dielectric screening, the state number, and the charge. Now let's work our way down to real systems of semiconductors. The effective mass goes down by an order of magnitude, and your screening goes up by an order of magnitude, and so you end up with excitons that have binding energy on the order of 10 eV. Now, in the case of 2D systems, it was shown here and in many other places that this binding energy is actually on the order of half an eV. So what was done in this paper is that you can observe the ground state and the excited states of the exciton, just like the way you think of the hydrogen atom, 1s, 2s, and so on. And experimentally, this should converge towards the quasi-particle edge. And by looking at this from the ground state to this, where this, the states are converging, you can read out this number of 300 MeV, and that's the binding energy in the system. An important thing to note here is that this is a consequence of non-local screening. So your ground state sees quite a bit of the material, and as you go to the excited states in the quasi-particle gap, they're sensing mostly only the environment. So to summarize, here you have your exciton sitting in your 2D system, and as you change the Bohr radius or the distance between these carriers, you have a series that's highly non-hydrogenic, and you end up with a system that has a binding energy of about 500 MeV compared to bulk semiconductors, which were on the order of 10 MeV.
And the gap width is what?
I'm sorry?
The gap width.
Gap is 2.4 eV.
So do I understand you correctly
Yeah.
that the exciton binding energy is about 1/4 of the width gap?
Yeah.
The gap, and you still think that the effective mass approximation would work?
No, so it's not a. You use a you use the Keldysh-Ritova.
No. Keldysh basically tells you that it's just short distances, interaction is logarithmic instead of the Coulomb interaction.
Right.
But there is a kinetic energy part, and for this you are using still gradient squared.
Okay.
Despite the fact that the kinetic energy is already very substantial part of the width of the gap.
Right.
Okay, which basically means that the exciton radius is a few lattice constants, right?
Yeah, it's a nanometer.
All right.
Yeah.
So then the question is, why you think that the pitch of the weak coupling excitons, which is not 1 year, is more applicable than the starting point of the Franklin exciton?
Right. So it's in between. So it has a very strong binding energy, but at the same time, it's also delocalized in this lattice. So
For how much? What is the characteristic radius of the exciton, according to you?
What radius?
What is the radius of the exciton?
It's about the Bohr radius is a nanometer for the ground state, and as you keep increasing the state number, so as you increase the state number, it becomes larger than
right.
Correct.
Right, but the ground state exciton is really exciton is really an exciton of the small radius.
Yeah.
And why do you think you can still describe it? It's a quadratic spectrum with a logarithmic interaction.
So if you look here, if you go to the lower state number, this approximation falls off. But at the higher state number, this approximation is better. So you have to use this. So obviously the 2D hydrogen does not fit for this lower state number. So it's an ad hoc. So here, what they've done here is showing just the screening that they use for the lower state versus the higher state, and this changes. So you're right that this approximation is not correct at this limit, but as it becomes larger and larger, it becomes more appropriate. That's what the red line, which is the 2D hydrogen, shows, and this theory is not that.
Yeah, I know what this is.
Right. So what we're going to do is use this to probe the band gap. And so as I was describing earlier, if you have the ground state, it senses your material and a little bit of the environment. As you keep increasing the state number, you sense more and more of the environment. And using the difference between the ground and the first excited state energy, you can read back. The binding energy, of course, there's theory that goes into this, and the band gap is the ground state plus this binding energy. So this way we can extract the quasi-particle gap without, only through optics. So the experiment is fairly straightforward here. You use white light and you measure the reflectance contrast spectrum of this. So it's like measuring an absorption spectrum in this case. And you have a sample, something like this. Of course, samples have improved over the years. You can make much larger ones now. So you have WS2, it's a monolayer of the semiconductor that's in blue, sitting on top of the transparent substrate, and we partially cover it with graphene of different thicknesses, and we go from spot to spot. We are limited by the diffraction limit here, so something like a micron, and measure the exciton states in these different dielectric environments. So for all practical purposes, you can read this reflectance contrast as just the optical absorption here. So if we look at a system that's here, you have a WS2 sitting on hexagonal boron nitride and graphite. Here's some data at room temperature. So you have the A and the B exciton, which is just the spin splitting of the tungsten. But what I want to draw your attention to is this little bump that's in between here. So this orange line is the WS2 sitting on Bn, and so you have a delta 1,2 that you can see that's on the order of 100 MeV here, and as you move the spot from this part of the sample to here, and you measure the reflectance spectrum on graphene, what you observe is that this delta 1,2 reduces, and also there's a little bit of a change in the 1s state, but a greater change in this delta 1,2. And this already tells you that the nature of the excitonic states are changing, and also the band structure should be changing. The band gaps should be changing. Now, just in this case, we're plotting delta 1,2 on the y-axis and the number of graphene layers on the x-axis. If you have no graphene layers, you have this delta 1,2 of about 160 MeV. That's the experiment is in circles. And the moment you add a layer of graphene, this goes down to 100 MeV. And after that, experimentally at least, the effect more or less saturates immediately. And using the theory where they're simulating this dielectric environment of this nanostructured dielectric environment, we fix the parameters for the pristine case. This was a collaboration with David Reichman's group. And then after we fix the parameters here, we just add the screening and see how it changes. Now, to move away from that picture, now we have the theory, we can actually plot it directly on the energy scale. So we have the 1s, this is experimental data that goes from 2.1 to a little bit lower. There's a few tens of MeV change in the external spectra here. But if you look at the quasi-particle gap or the band gap, this changes by a lot more. So you start with the binding energy on the order of 300 MeV, and you reduce down to close to 100 MeV here. And this is also indicates the nanoscale sensitivity in the out-of-plane direction. So we still don't know how sharp it is when it changes in the in-plane direction. So to summarize, what I want you to take away from this is that if you have a monolayer of a 2D material and you were to place this graphene on top, for example, or an external dielectric environment, you can create a potential well in this system without really changing anything in this material itself, ostensibly. So you, and this can be on the effect of on the order of 100 MeV. The limit would be close to the binding energy, and also this change will scale with the binding energy. So if you have a system like BN that has a binding energy of an EV, this effect will be even larger. So also the exciton does change as well, but it's a weaker effect because it's sensing less of the environment. And it's like having a junction between two materials. The only thing is right now we don't know how sharp the junction is because we're limited by far field optics here of our micron resolution. So I talked to you about the vertical transitions in these materials, which related to just the band gap, but I was suggesting that this is non-invasive, that you're not really changing the band structure. What's the evidence for that? There's no direct evidence from the optical spectra that I have here. So what I decided to do when I moved to Berkeley, because they had this very nice user facility up at LBNL, at Lawrence Berkeley National Lab, of doing angle resolved photo emission with spot sizes comparable to far field optics. So with in this measurement, what we're doing is striking our sample with high energy X-rays, and then measuring the electrons that are knocked out of this sample, and it has enough energy and momentum, and you detect it in a hemispherical detector, which gives you this information. And again, the neat thing here is that they can actually vary the spot size really to do correlated optics with RPES here. So again, the same sample. So this is the sample that I showed you earlier, that you measure the exciton state. So this is the 1s, this is the 2s. And on the exact same spots, we again measure the RPES spectrum. So this is on BN, and this is on graphite. So just to orient us, what this, how to read this photo emission intensity. This is this part of the sample here. So this part of the spectra here is related to the valence band, and the spin splitting that you see here is related to the K point, and this is the gamma point. So essentially, the main or the primary effect here appears to be that you're just doing a scissor operator on your band structure. So you're just shifting your energy levels rigidly. In fact, if you were to calibrate your spectra with respect to your core photo emission, so you have your photo emission from your tungsten 4F that's deep inside, and you can overlay the two fits to the photo emission intensity, and within 10 MeV, you see that it's essentially unchanged.
I'm sorry. Can I ask a question? So this is capped. You're looking at photoelectrons that go through the cap. No, it's split.
Yes.
I see.
That's good. Yes.
I see. So the dielectric environment is below.
Yes.
I see.
And we also have to do the perfect calibration for the band alignment. You need the secondary electron emission, which is not here. So what I can tell you right now is that it's a rigid shift, and that it's in fact you're not really changing your band structure, and it is in a way a non-invasive.
But the I suppose what I was trying to understand is that the photoelectrons only come from the dichalcogenide. They don't come from the layers beneath.
Actually, you can see a little bit of intensity from the BN. So it's only half a nanometer, so you definitely see shadow bands from underneath. But they're not hybridizing in any way. So yeah. In fact, now people are suggesting putting a monolayer of BN on top of your sample and then doing the photo emission is even nicer because you lose some intensity, but you gain in sharpness of your line.
And the fact that you cap only from one side as opposed to the other side, does that screen efficiently the exciton, or would it be better to? I mean,
if you had it on,
notwithstanding.
If you had it on both sides, you'd have more screens.
I see.
This is true.
And that means that this guy would shift more, or it would be more. I mean. So, what's the difference between two caps and one?
So I have some data in the backup that I can show you, but basically it would be another 50 MeV. With, say you were to encapsulate the whole thing with graphene, then you'd get one layer of graphene on one side, one layer of graphene on the other side. You do more than 200 MeV of renormalization, whereas on just one side you are like closer to 150 MeV. So we collaborated with Tim Wheeling's group, and our main collaborator here is Malta Rosner, who used to be at CCQ, and he calculates the G delta W in the G delta W approximation, where we use an effective dielectric function, and for different screening, the band structure itself again doesn't really change in its theory between the grayish blue and the grayish orange, and we're just plotting our experimental results on top here. The bottom line is that you can have very large variations of the band gap due to screening, just purely due to screening, and almost no change of the dispersion within 10 MeV in our.
So where do we see the changes in the band gap from the calculations here?
So this should be, actually you don't see this here because we kind of cut it out.
I'm sorry.
Yes.
Those orange dots are
Yeah.
the data from Marcus.
That we have to correct for some detector.
What is the error bar?
Error bars would be, so this would give you an idea of the error bars, about 20 MeV.
So do I understand that correctly that error bars are actually wider than any features on the graph?
Oh, no, error bars are smaller because this is EV here.
Oh,
This
I
is
see.
plot on EV,
I see,
so error bars are much smaller.
Sorry.
Yeah, there's the systematic corrections, which are not error bars, which is part of the usual mystery bar.
Right.
But what you're saying is that, in essence, these curves have been shifted somewhat for the two different cases, and that's why we don't see the change in the band gap.
So
Or the
this
change
would
in the
be,
band
so I
gap
would
is
say
really
the band
a little
gap change is
different.
actually here. You can see
Okay,
the change
okay.
between these two lines.
Right.
It's just not the right scale for that. But yeah, so this is EV, so your band gap change is embedded here.
Okay.
So to
So
summarize,
is charging of the sample an issue? I mean, of course, you change the dielectric environment,
So
so
the
your
thing-
photoelectrons will also experience that. Yeah,
so it's insulating, right, BN underneath.
Exactly.
So this is a bit of a mystery. We have this whole thing sitting on top of a monolayer of graphene, and it really works well that there is no charging. So something basically, when you hit it with 145 eV, that was the optimized X-ray energy for best matrix elements, but you see that from the graphene you can replenish through the BN.
I understand, but as you change the number of layers and the caps and the things, isn't it that the charging is going to depend? I mean, I don't mean to imply that the data is not right. I'm just
Right.
wondering.
So there's no cap on top, right? Again, this is for
When you compare the sample,
Yeah.
the pristine sample to a sample in which you've engineered the environment,
Yeah.
doesn't the charging of either one of the two samples change subtly? And hence the shift, that you have a rigid shift of
Right.
of
So
function.
here
Yeah.
you can read out a little bit about the doping. So when you say charging, that there's some residual doping.
No, I mean your sample floats. So when you look at the photoelectron total energy of the
We never
photoelectron
look at the
detector,
floating sample. We never look at a floating sample.
floating meaning the sort of the voltage at which the sample sits
Yeah.
changes a little bit when you ionize it,
Yes.
and it changes by an amount that depends on the details of the dielectric. And so that
Yes.
gives you some uncontrolled rigid shifts on a quantity that I don't know how big it is.
Right,
That's my
right. So
question.
we
Yeah.
use the secondary electron as the reference for that. We use the secondary electron emission. You see a band in your, and that tells us if, so it does change. If you measure it for hours and hours, that secondary electron emission will shift, and we use that as a reference. That effect happens, and we just have to make sure we are within that.
Okay, so now,
Yeah.
before you go on,
Yeah.
so you said that you had in effect a junction
Yeah,
in some of these experiments.
Yes.
So there's an edge, right, between the two materials.
Mhm.
Does that edge support any interesting excitations that are localized to the edge, whether plasmons or something?
Yeah, Malta would say so. So in the theory, there's on that line of the bare BN, which has been chopped in different ways. You can chop it armchair, zigzag. He would say that there is, say, metallic states, for example, that can come about. But we have no way to, in our measurement, we have no way to see that. But it is true that there is.
What would be required? I mean, again, what I guess I'm interested in is if there are localized excitons or other optical excitations.
Across that boundary.
Well, that would live on the boundary, basically.
Yeah,
Actually, I have a question.
Yeah.
The Coulomb interaction changes not only produce the bound state, which is acetone, but also change the form
Of the
edge, which is known as the field enhancement factors.
of the edge.
Yes.
Yeah.
The edge of the spectrum that instead of three dimension, instead of drop,
Mm-hmm.
you actually have an enhancement and
Mm-hmm.
then sharp drop. Is there any evidence of the enhancement on the edge of the continuous spectrum?
We never measure the quasi-particle edge in the optical spectrum. Yeah, because the oscillator strength is mostly residing in the excitons, and then you have so between 1s and 2s there's an order of magnitude difference. So that's why we have to use this delta 1, 2 and the exciton positions to extrapolate, and that's why we need the theory in between. So we never really, there are some papers that claim to see it like very early on, but now it's very clear that, especially with the BN encapsulated samples, or even you see only a series of the bound states that just when the oscillation disappears. So just to, since Professor Millis brought up this question, there's a number of interesting future directions based on this. So what is the length scale on which this, the band gap is changing? Again, from theory point of view, the self-energy changes within a few unit cells. That's huge change of 100 MeV within a few unit cells. We haven't really probed that yet. Again, I said it's non-invasive. I said, okay, it's a rigid shift. But then what about if you tune electron-electron interactions, you'd expect some structural changes. What exactly are the details of that? That's also unclear. Is it a type 1 or a type 2 heterojunction in the sense that does the valence band move more or the conduction band move more? And also, how do we understand disorder that could arise because of this is few future directions. So the second,
I'm sorry, Sam, also, I'm just curious about what's possible from you experimental wizards. I mean, in particular, if there were, for example, a localized excitation at the boundary between these, what length scale would it need to be for you to see it? What's feasible for actual detection?
So, I mean, I guess near field techniques might be interesting for looking at the boundary, but just from my point of view, far field point of view, I would think of, say, maybe it could come up in the chalk talk thing, but maybe just designing the dielectric environment with, make pitches, and you vary the pitch, and both in the ARPAs and so you maybe patterning the dielectric environment in a clever way would help us probe it from the far field.
Right, I got it. Okay, thank you very much.
So this part is, so moving on to my second part of the talk, which is about energy transfer from quantum dots to 2D materials, where the effect of screening would again come into play. So quantum dots are core shell and semiconducting quantum dots have been known for 30 years, and they're now highly optimized with almost 100% efficiency. That means if you were to excite them, you'd recover all the energy in the emission. However, the caveat in this is that these quantum dots localize their carriers in this structure, and that's one of the ways to improve the efficiency. So something that when I started looking at these materials is how can you extract this exit energy from the quantum dot outside. You can think of charge transfer, but that would be very inefficient with a very thick shell and exponential current. But one way to do it is non-radiative energy transfer using dipole-dipole interaction. And we had 2D materials lying around as well, so why not couple it to these two? So we had a system where you had the quantum dot emitting at around 2.1 V, and this is absolute absorption of a monolayer of MOS2 and graphene, and we put it on these two different materials. So just looking at this data here, you'd say that MOS2 tends to absorb more, graphene a bit less, in the region where this quantum dot has the dissipation, and maybe MOS2 would be better at this dipole-dipole interaction here. So our first experiment that we did was just look at the wide field excitation maps of these single quantum dots that have been very dilute quantum dots have been spread out an insulating substrate. Just pay attention to this scale bar here. So in this photograph of the quantum dots, the main process is you come in with a laser and you're measuring the radiative decay. Now, when you put these dots on a monolayer of graphene or MOS2 here, this emission really goes down by an order of magnitude. And we were wondering what's going on here. So the best way to measure this is through time-resolved photoluminescence. And so we'll measure the emissions as a function of time, and the decay rate will give us information about the rate of the process that's going on. So in terms of the data, we have quantum dots on a substrate. So this is the decay curve over many nanoseconds, and the instrument response is much sharper. So we're confident we can see these emissions very well. And when we do the exact same experiment sitting on top of graphene, monolayer of graphene, the decay rate goes up by an order of magnitude. That matches with the light emission going down by an order of magnitude in those wide field maps. And we do this experiment again with increasing number of layers of graphene, and this saturates very quickly to a value within a few layers. And more graphene layers, more efficient is this decay rate or this energy transfer rate into this material, and that seems reasonable. However, when we did this exact same experiment on MOS2, we observed the opposite. So if you start with a monolayer of MOS2 and you add one more layer, the energy transfer rate or this non-radiative energy transfer goes down by an order, starts decreasing. So this is just a guide to the eye, but to plot the data points here, so you have, even at the monolayer limit, graphene is more efficient at this energy transfer than MOS2. And as you start increasing the number of layers, they show completely opposite trends. And this went against our intuition at the start. So before I show the comparison with the theory, and I wanted to motivate the sort of the physical picture here. So we can simulate such systems in some finite element software like COMSOL. You have a dipole sitting on top of a layer of a dissipating layer. The electric field of the dipole is impinging into this material. If it's more red, that means there's more efficient decay into that material. And if it's more blue, it's lower. So forget about if it's graphene or MOS2 for a moment. So you have something dissipative, and this is a insulating substrate. The moment you add more layers of something that's highly polarizable, you are automatically going to reduce the overall field intensity in that dissipated layer. But now the question is, in a very naive picture, if you were to think of energy transfer as this dissipation or absorption times the square of the screened electric field, as you increase the volume, you're increasing this integral, and so your energy transfer rate is going up. But in case of MOS2, what's happening is that addition of even one more layer reduces this field by such a great amount that the increased number of dipole channels for decay channels you're adding here doesn't help. So in case of graphene, sure, the field can go down a bit as you increase the number of layers, but overall what wins is that you have more absorption underneath. But in case of the MOS2, you're even adding one more layer screens it so much that you are losing from the start here. So actually, the data was again, we collaborated with David Reichman's group again in this case, and we treated the quantum dot as a point dipole, and the dielectric 2D material is just a slab. It's very classical in that sense, and the inputs were just the dielectric function, the quantum dot size, the acceptor thickness, and using the decay rate in the solution, we can just get the numbers out. There are no free parameters here. And so this was theory that was originally developed by Chance, Proc, and Silvey in the 70s, and sort of more recently adapted here for 2D materials. And what we see is remarkable, sort of within a factor of 2, not only the trends, but also the absolute rates. So, but what is still missing here in the story is why does one behave in one way? Can I tell a priori what would be better? Which type of behavior arises if I give you a dielectric function? And this is not something that was easily tractable from the analytical form of the equations. So what we did was the next best thing. So we came up with a metric.
Can I ask you
Yeah.
about your model? So
Yeah.
are you really adding layers here, or you're changing the slab thickness? And are you
Oh,
considering
so this is just converted to number of layers. We are just changing the slab thickness. It's like
so there is no anisotropy in the system?
No, there is because of the dielectric function. So I'm supplying epsilon in plane and out of plane. So the anisotropy for that slab is there from that. But otherwise it doesn't. It's really classical. There's only like a continuous slab, and that's why it starts at 0 here.
Can you put this or compare this for me in the context of a Purcell enhancement of the decay rate or something in a cavity? Or, I mean, is this
Right.
in any way related to, yeah?
Yeah. So when we that's sort of taken into account here when you're changing the epsilon, you are changing the radiative rate as well, and that's not as strong an effect here as the change. So for all practical purposes, this dramatic change in the energy transfer rate is not due to any of this Purcell enhancement. We include that in the calculation. It comes in as just this effect of epsilon.
But I
Yeah.
suppose what I'm trying to understand is in what way is the physics different?
Oh, the physics is different because Purcell is related to the radiative rate of your exciton in the middle.
And this is
This is
non-radiative.
not. This is related
Okay.
to extracting it outside.
Fantastic. A related
Yeah.
question. Can you
Yeah.
put this in the context of a Fano reshaping of the line then? Either way.
Yeah, I mean, maybe the best, the quantum dots were not the best system for that because we're sort of looking at something that's inhomogeneous already on this. But yes, the absolute absorption at each dot, there will be a change in the.
No, what I mean is that if this is not it's not an issue of radiative decay, but it's a non-radiative decay.
Yeah.
Can I think of this as some sort of dressing of the energy level of the quantum dot by some continuum?
I mean, yes. I mean, I guess that is what is happening here. But when you say some continuum, it's a very specific continuum here.
I understand, but is this a Fano effect or not?
I actually wouldn't say so. Yeah.
So if it's radiative, it's a Fano.
Yeah, if it's non-radiative, it's not.
Non-radiative, then it's not. But
Yeah.
just following up on this
Yeah.
question, if I put a dipole on a dielectric, passive, nothing to do with non-radiative, a high index dielectric, I would expect that it would change my photonic density of state in general,
Yeah.
and that it would affect by a factor of 2 easily
Yes.
the radiative rate. So I know, or the PL. So why do you say with so much confidence that it is a non-radiative as opposed to radiative?
Because we did the simulations for it as well and the analytical form as well. Because if you had a uniform dielectric, say, of this epsilon of MOS, you're just embedding it, the whole thing. But it had no.
But remember,
the
the dielectric of MOS2
Yeah.
around is huge.
Yes.
Yeah.
But so is the imaginary part here, right? So the dissipation is winning overall. So I think that's the case. And also the reason the radiative rate is not changing as much is because it's really anisotropic. So you're only seeing it on one side, and this is also embedded in like 10 nanometers of zinc sulfide or something like that. So by the time it sees the change here, it's a much weaker change in the overall effect. So in this COMSOL simulation, we could include, so here we are not including the shell effect and so on. There are reasons why this is obviously not exactly agreeing with theory, because there's 5 nanometers of this zinc sulfide shell, and then there's a nanometer of your ligands, and then only you're seeing your high dielectric, so to speak. So you're right that it does change the radiative properties or the Fano effect, but the primary effect here for the change in the recombination rates is actually not radiative in nature.
Okay, I guess I have a related question. Where does the energy go?
Into the 2D.
What is the final product? Electron hole pairs?
Yes, it's excitations in your.
The electron hole pairs?
Yes.
The graphene.
Yes, but then they recombine very quick, thermalize very quickly.
No,
Yeah.
And the electric functions which you're using, is it what you are modeling or this is what you are measuring?
It's experimental dielectric function at the quantum dot energy, at where the quantum dot sits. Yeah.
So this is measured from some other experiment?
Yeah, this is data that exists that we're being used for this bulk material. Yes.
How do you know the autoplane data structure for these few layers?
Oh, we don't have to know for the, I mean, it's the same for the few layers in the bulk. The outer plane, there are like huge measurements down to fairly low energies. So experimentally, this has been known for many decades, the in-plane and outer plane for the bulk, and that's the number we're using. We don't, here the fact that it's, the change in the properties of the electronic structure as you make it thin is not important here. What is important here is the fact that you can just make it very thin, and then you're using just the dielectric functions from the bulk. So, of course, it would be good to, have this one metric where you can say, okay, it will behave this way or that way. We couldn't do that, so we came up with a.
Yes.
Yeah.
There is other possible process of non-radiative decay,
Yes.
which is other process inside the quantum dot.
Yes.
Which can be affected by the environment.
Yes.
Because it's affects the interaction inside the dot.
You're right. Yeah.
So what about this mechanism?
So the sort of the regime that we're operating in, the excitation densities, and so we can do a sort of as function of the excitation density, we have the results, and that's in a very linear regime where we don't have these other processes going on. So we just
process is not nonlinear, right? It's basically Auger process is not nonlinear. It's basically yeah, right.
So okay. So just to cut to the chase here, we don't have a good way to tell you which, if you want to make your new solar set or some stack of materials for your application, we don't have one parameter that just changes and tells you which way it behaves. But what we did do is plot the analytical function. We have a real part of the dielectric function here, imaginary part here, and the colors tell you the decay rate, maximum decay rate over the bulk decay. So if this number is equal to 1, it behaves like graphene. The more layers you add, the more efficient in energy transfer you are. And if it's greater than 1, it's more like MOS2. So just like here. So this would be like MOS2, this is like graphene, and this metric would be equal to 1 or greater than 1. Most materials at around 2 eV. So of course these dots will move around at different frequencies. You have different dielectric functions. Most materials are behaving like MOS2, like the technologically useful materials here. Just as an example, silver metal screens very heavy, it's metallic, it screens a lot. So a monolayer of silver or a nanometer of silver would be 1,000 times more efficient at this non-radiative energy transfer than bulk silver, for example. And sort of in the past as well, people have measured like energy transfer to silver surfaces in the 70s and 80s, and it essentially looks like a 2D sheet because you only see the first monolayer of it. So to summarize,
can you go back one? Sorry.
No worries.
Yeah. So for me to just take home, is there anything special about the 2Ds? I mean, in this whole color plot, if the 2D didn't exist, couldn't I do the same with a bunch of ferroelectric metals and
no, the reason the 2D had to exist here is because you had to make something that was half a nanometer to observe this layer, this thickness dependence.
But let's say I was able to make strontium titanate, which in monolayers, which I can do, or somebody can do.
Yes.
Would that do the same thing?
But it depends on the gap of, I mean, whatever. Yes.
Whatever. Some dielectric that I can grow in.
The ability to make something monolayer. If you can do it, it doesn't make the TMDC or graphene anything special. It's just that it was an easy system to show this.
Understood. Okay.
Yes.
Very good.
So you can have a really efficient energy transfer from quantum dots to 2D materials. The sort of the thickness dependent trends can be sometimes unusual, and we were able to explain this as a competition between the dissipation and the screening in these systems. and we made some predictions for other systems as well. So in the final part, in my remaining few minutes, this is fairly short. I just want to tell you a little bit about also how the local dielectric environment, or adding layers, to, increasing from monolayer to few layers, affects exciton-phonon interactions in these systems. So if you look at this, is again a schematic. You have an exciton in these materials, so you have a peak, and the radiative rate plus phonon scattering tells you something. The line width informs you about these processes here, the radiative recombination and phonon scattering. Now, when you add an extra layer, what happens? So you, of course, the electronic structure changes. But what I want to show you today is that going from indirect to direct gap itself wasn't the crucial aspect for changing the phonon interaction, but in fact, having this unique screening is what contributes to a change in the dephasing rate here. So we have a system like this. You have a monolayer of material, you have a bilayer of material. So this is in blue is the monolayer, it's fairly sharp, and the bilayer, you can immediately see that it's broader. It's a direct gap because it's the absorption and the emission here, they're pretty much the same, but the bilayer is an indirect gap. So initially, the first thing when we saw the data was like, sure, it's going from a direct gap to an indirect gap. That's why you have more efficient phonon scattering and dephasing, because you have more density states to go into. But we looked at statistics. We, of course, during a PhD and a postdoc, you make many samples, and we looked at the line width statistics of many of these samples, and we saw that, in fact, there is a statistically significant difference of about 50 MeV, which corresponds to processes that are on the order of 10 femtosecond that are going on between this monolayer and the bilayer. And we wanted to understand this better. So in the single particle picture, just without turning on the Coulomb interaction, and there's no spin orbit spin, I'm not showing it here, but you have the band structure like so. You have the direct gap at the monolayer, and you have essentially only scattering from K to K prime and within the K value here. Now, when you add Coulomb interaction, however, we showed a few years ago in an experiment theory collaboration with Andreas Knorr and Erwin Lalich, that you, in fact, have a new dark state that arises because the lambda Valley effective mass here is it's heavier, and so you have higher exciton binding energy, and so you have essentially a new dark state that forms into which this direct exciton can decay to. Now, in case of the bilayer, just to repeat the point that I made earlier, it becomes an indirect gap material, and there's this new transition, that's the lowest line transition, and you would think that the moving from K to gamma, the whole, so that's why it's in the opposite direction, the arrow, would be the dominant interaction. But what we found is that it's a completely different phonon mode that contributes to this. So that's the sort of the take-home message is that you can have new processes that arise because of the screening, which were not present previously, and that can tune your phonon interactions with your exciton. So you start with the direct gap at the K point, so you have dephasing processes within the K valley or to K prime. So you have this both in the monolayer and the bilayer, which are color-coded in blue and red. And now when you go to the bilayer, you definitely have this additional process of this indirect gap coming here. But what the results will show is that this new dark states that form due to increased exciton binding energy at these lambda points contribute the most to this line width increase. So from the 50 MeV, most of it actually comes from this and not from these processes that one would have assumed to be more important. So on in the theory side over here, so the carrier phonon interaction matrix elements were taken from previous work, and then the problem was solved to create these maps of the line width versus temperature. This is all pure theory. And so you have the radiative rate that's over here, and then you add on the different K to K scattering, K to lambda, K to K prime, and this is what it looks like And if you were to add these processes that involved this K lambda prime and the K lambda prime here, you get this huge increase in the line width. And in fact, when we plot the total line width from the theory on top of our experimental temperature dependence, what we see is that this is in fact what's going on. If we didn't include this channel of the new dark states that arose from screening interactions, we'd be missing about 30 MeV or 40 MeV in each of these cases. So with that, like, I just want to summarize because my time is almost done. When you go from direct to indirect gas material from the monolith to bilayer, you have to still consider the Coulomb interaction for scattering processes. And because of that, you're actually adding this extra line with a 50 MeV in the bilayer materials, which would not be the case without this the renormalized interaction for the excitons. And the single particle picture would not give us the direct correlation to the experimental results from theory. And at the end, there are new lower lying intervalley states due to the screening effect. So at the end, I just want to, in my last minute, I just want to leave you with the picture that you have this atomically thin canvas, and you can essentially pattern either new materials on top, or you can pattern more complex materials on top. But at the end of the day, you can just tune electronic structure and create new kinds of heterojunctions by not changing the material itself, or change the energy transfer rate, or change exciton-phonon interactions, but by purely changing the environment. And that way you can control where these carriers are going from one place to another. So the three parts which are related to band gap renormalization, energy transfer, and exciton-phonon only form a subset of the kind of interactions we can think of tuning with the environment. More recently, there are other elegant ways to do it, like invoking Mori potentials, for example. And so I think there's a lot to do here. So thank you very much for your time. And the most important slide, of course, I presented works that I led, but it was not, in isolation. It involved a lot of people, especially theory collaborators in the Reichman group. Alexei was a postdoc in Columbia. Lutz, Eli, Aaron, Chris, and Roland at LBNL at ARPAS, Jim Hohn's group who taught me how to make samples, Andreas Knobner and Monis's group for the phonon theory, Malta, Christina, and Tim for the art part. So thank you very much for your time.
Okay, great. So, more questions. We had some during the talk, but
when you're saying about phonon,
Yep.
which phonon?
So in this case, in this particular case, there was a M phonon. That was, sorry?
Which is what?
Which is basically a phonon that connects this K and the lambda prime values. That was the most important phonon. You can also see this from Raman measurements. So it's an optical phonon that sort of is turned on because of the screening interactions that lead to this value being lower. So you see enhanced Raman emissions.
But may I ask, why is it so strong temperature dependent? I mean, this is an energy gain process, right? The dark state at lambda prime is lower than the, so you can just have a phonon emission. Is this just the Bose factor, which is that the emission is more as you raise the temperature because?
So that's true that in case of both, so the biggest difference though is at cold temperatures.
Mm-hmm.
So, and then you have over and above that this energy gain, which is almost equal in contribution. So you're right in that case. So,
okay, but
so low temperature is purely due to emission into the dark state.
Okay, so
Yeah.
the difference between 5 to 10 and nearly 40
Yep.
is the presence of the dark states and simply spontaneous emission into them.
Right, that would be in this case.
Yeah.
And then you have just the temperature after that come up over here.
They have the same reflection symmetry keyboard, right?
Mm-hmm. So, I mean, so sort of the way we want to take this next would be to look at, also as a function of angle, how these line widths are being tuned, because not all of these will be active then. There might be like a particular, so not these very magic angles, small angles, but just a way to tune line widths itself. And I think the natural bilayer system is just the starting point of understanding what's going on. Because initially we were just convinced that this was all due to just the indirect gaps, but it turned out that's actually just 1/5 of the contribution, so to speak.
It reminds me of one more thing.
Yeah.
My recollection was that in the very beginning, people were thinking a lot about spin-orbit splitting near the key point, conduction bands.
Yes.
In the valence band.
That's a different dark state. Yeah.
Now, in your talk, I haven't heard a word about spin-orbit splitting.
So
the difference between theories.
So in the sense, it definitely exists. It's just that I didn't necessarily probe it or use it, because one thing is in this linear optics regime that I'm working with, I'm not going to probe that directly. So so there are some effects of it. For example, the photoluminescence yield, if you measure these materials, it will change because of this spin orbit splitting. So the tungsten would be different from the molybdenum, but those were not the physical processes I was concerned with here.
Yeah.
So in MOS2 there is no dark state. So in MO there is no dark state, but in W there is. So that will affect different types of properties compared to what I was discussing. And one of the reasons also I chose tungsten for most of my talk was because the spin orbit splitting is large, and I could observe the excited states comfortably. Even at room temperature, I could see a big sharp peak in the middle, which you can't do when you have the smaller spin orbit splitting. So it was a choice of material for practical reasons as well. But definitely there are a lot of interesting things to do with the dark state, and people are looking at modes to go in the plane of the material itself. And yeah, it's just something that I didn't work on here.
Okay, other questions? All right, well, let's thank Archana again then. So, and she'll